The slides are, as usual, not mine. This one comes from Yandex Research. And today we are talking about different approaches to scaling reinforcement learning and any machine learning. So we are not going to focus on methods that only work for machine learning. The methods we're covering today mostly work for any like training of neural networks, and scaling them beyond one machine, one computer, and one GPU. So if you need to train a neural network on much more than one GPU, and there are good reasons to. Basically, the good reasons come down to the fact that our data set never fits on one GPU, and more crucially, our models can also have trouble. We can also have trouble fitting them onto one GPU. So this illustrates the size, like the average size of models in various tasks. So we have image classification, we have machine translation, and the trend is basically that models are getting bigger and bigger, and the newest models are often impossible to fit onto the memory of even the newest GPUs. Basically, the issue is that the size of our models grows faster than the size of our GPUs. This is a slide by Microsoft, where they really want to drive the point home with their new TNLG model with 17 billion parameters. This is the language model recently published by Microsoft. And yeah, we have in every area of machine learning, we have some super tasks that really make it, that really push against our computational resources. They are the kind of tasks that are still underexplored because they require a lot of compute. And in reinforcement learning, these are tasks like playing games from Steam, so not games that we have cherry-picked because they're easy, and playing those games only using the video stream and some architectural convolutional neural network to understand what's going on there. So what can we do? What are we to do? Well, the first and most obvious thing to do is to run data parallel training. It's because we definitely know that our data set isn't fitting on one GPU. We always, even if we have one GPU, we are still batching our data. So even with one GPU, we had to cut the dataset into batches and run them sequentially. So there shouldn't be too much of a step, too much of a leap to go from from sequential batching to processing batches in parallel. So we can cut the dataset into several parts and train a network on each GPU on a part of the dataset. So here we have, in this example, we have 4 GPUs, and we are splitting the dataset in 4 parts. And then the biggest issue is what do we do when we have trained a network on each of the GPUs? What do we do with these different networks? So we if we do even one training step, sort of forward step and backward, forward propagation, back propagation step. After that, we end up with 4 different states. We end up with 4 different parameter sets. And then we have to, either we have to do it every time, or we have to do it in the very end, but we have to somehow join the results. And the naive and the simplest approach is to sum up, to have some central node that is going to store the sum of our gradients. So joining a neural network at the very end of the training is a bad idea because we are going to have specialized neural networks, and essentially we're going to get an ensemble. And this is definitely one way to go, but we would like to train a single network and not an ensemble for a whole host of reasons. A simple reason is just it takes less memory. And to train a single network, we would sum up the losses, sum up the gradients every time on some central nodes. And then we apply. So when we are doing, in PyTorch terms, we are doing optimizer.step. So in mathematical terms, what we're doing is we are adding, we are subtracting the gradient multiplied by learning rate from all the parameters. And so this subtraction will have to happen jointly. In order to keep training the same neural network, we have to do the subtraction jointly, but at least we can calculate the gradients separately. So we are going to be calculating the gradients for every part of the data set on a separate node, and then summing them up. And then on a central node, we are going to jointly apply all of the gradients. Now, there is no real reason here to have a separate central node, right? So we can the node that is going to sum up all of the gradients, the node that is going to do the job, it doesn't have to be a separate node. It can be one of the GPUs. So there is no reason why this would be a completely new node. We can give one of these nodes the job to sum everything up. Or we can think of a reason, we can think of a way to synchronize, to do this operation without centralization at all. So here we are represented by this magical box. So on every GPU, we have gotten its own set of gradients, and then we are applying some magical box to make sure that after this magical box, every GPU has the same set of gradients, and the same set of gradients is the sum of these ones. And what we've seen on the previous slides, here, is a specific case of that magical box. So this is one way to make sure that after the central node does this and sends it back, replicates it back to all of the nodes, we end up with the same value. But it doesn't have to happen with a central node. And the reason why we are separating it with decomposing it into this separate magical box is because this problem has been solved a lot of times previously in the field of parallel computing. This is basically a separate solved problem. And so by decomposing it this way, we can just say that look into the parallel computing literature, or if you are more practically inclined, look into the parallel computing libraries and get a solution for the all-reduced problem. I'm going to cover shortly like how this can actually work inside this synchronization. So naively, what you can do is you can pick one of the GPUs to be the node that sums everything up. This is the same thing as we've seen previously, but the summer up is not a separate worker, but it is one of our GPUs. But it doesn't give us a lot of advantage in terms of speed, right? It's the same operation, it's the same sequential way to do it. And it's a lot of data exchange. A way to do it, I can stop here. Actually, I can ask you, can you come up with a way to do it better? Any takers? You can write in the chat or you can unmute yourself. Sharding, that's what I'd like more details on that. How do you exactly implement it? But basically, yes. We can separate our set of GPUs into shards, so into subsets, and the subsets will each subset, each shard is going to have its own leader that is going to sum up the values in this shard. And then this is going to be sent to a central node to sum it up completely. And then our operations, if you think about it, the sum operation here, we illustrate it as 1, but it's actually a lot of small plus operations. So if we do it this way, we actually have all of the plus operations distributed more equally across the network. Of course, you should do this only when you have a lot of data, because if these are if every GPU computes one gradient of size 1, so one derivative, one number, then all of the message passing that we're doing here, which will be much slower than the gains we've gotten by distributing the plus operations. But we are aiming at working with really big data, and with big data, this can be really helpful. And then, of course, this can go into more layers than 2. So we can have shards of shards and so on. Another way to do it, and this would be probably the most elaborate and in many cases the best way to do it, is to allocate, is to make every GPU the summer GPU, not to be confused with the season, a leader GPU for a particular part of the dataset. So we're splitting the dataset into, in this case, 4 parts, and every GPU is responsible for summing up that part. So everyone sends every GPU has all of the data. Oh no, actually they don't. They have okay. So we are splitting the data into chunks on a different. So it's important to understand this part, that we are splitting them into chunks on a different axis than the one that we use initially. So if we are doing data parallelism, and every GPU gets its own part of the dataset, in this case, in this simple case, every GPU is working with a section of the dataset, with 1/4 of the dataset. But here, we are also splitting it into another dimension. So we're splitting it into 4 parts on in this case, layers of the neural network. So the beginning, A is the beginning of the neural network, and D is the end of the neural network. And then each GPU is responsible for outputting the sum over this part of the neural network. And then what happens is to get the sum over the first part of the neural network, you have to get the first part of the data set over the first part of the neural network, the second part of the data set over the first part of the neural network, the third part of the data set over the first part of the neural network, and the fourth part of the data set over the first part of the neural network. And all of this gets sent to the first GPU. And the first GPU sums it up over all of the data, but only for the first part of the neural network. And then the second GPU does the same for the second part of the neural network, and so on. And this way, we achieve maximal distribution, maximally equal distribution of plus operations over all of our workers. And then when these components have been calculated, they get sent to each GPU so that each GPU has all of the information. And this is no longer a sum operation, this is concatenation operation. Because you need to concatenate the sums over the beginning, the second part, the third part, and the end to get all of the sums. And this is how it's typically done. There is a little bit more complicated version of this algorithm for a ring architecture. It differs from this architecture in that in this architecture, every GPU is connected to every other GPU. But in a ring architecture, a GPU is only connected to its two neighbors. And so you need to modify the algorithm to accommodate for that. I'm not going to go deep into ring all reduce right now. There's a link in the slides, and I've sent a link to the slides itself into the chat, so you can explore that. But basically, using one of the algorithms we're talking about for all reduce or one of the others, there is a weak part in all of these algorithms is that they don't think about any failures in the system. So they don't even try to think about reliability and what if one GPU doesn't work. They assume everything works perfectly. So if you want to think about fault tolerance, you would have to come up with take more complicated algorithms, but this is still like a family of algorithms that we call all reduce. And by applying that, you get the same gradients on all of your machines, and then every machine applies a gradient step with the sum, and training continues in a synchronized way. Now, one issue that we haven't addressed yet with this is that they are not. So this is the beautiful picture that implies that everything happens at the same speed. Forward pass, backward pass, we've got the result, and each GPU has got its result at the same time, at the same exact moment. And this is not what typically happens. Typically happens is that someone's faster. Well, usually it's not due to the GPU itself, but probably due to network delays. But for one reason or another, there will be a difference in speed, and there will be a big difference in what is ready when. And then everyone has to wait for all of the GPUs to finish to apply all reduce. So we would like to do something about it. We would like to do something to avoid waiting for all of the other GPUs. So we might want to apply some smart technique that lets us not wait for all of that. And in this case, we have 4, but in reality, we might have 50. So we need some technique not to wait for all of the other GPUs. And as it turns out, the technique is just don't. The technique is just instead of waiting for the synchronization step, instead of waiting for the synchronization step and then sum it all up, we have central we have a central parameter server. We have a place where all of the parameters are stored, and we do everything asynchronously. So we don't actually synchronize the GPUs here. Every GPU makes a forward pass, a backward pass, calculates the gradients, and then does the optimization step and applies and subtracts them from the parameters in the central node. So they're subtracted in the central node, but everything else, all of the calculation of the gradients happens on the workers. And so, can you see what the problem is here? So we've just taken an important step, like waiting for the other GPUs and synchronizing. We've just taken it and decided that, why do we need it? Like, we don't. Like, what the hell? Let's not do it. What do we lose here? That's so Sander raises the point that we might override the parameters. I would like to separate the two issues here. So there is the problem of the atomic subtraction. So if you think about how subtraction works, when we subtract the gradients from the parameters, then we have to first read the parameters, then do the subtraction, and then write the result. And so if something happens in between, in between reading and writing in this case, then this operation will be completely forgotten. Then some of our operations will be completely forgotten. That's a problem, but that's not a hard problem, because if we can make subtractions atomic, so we can just tell our parameter server that let's wait, but only for subtractions. So when someone asks you to subtract these gradients, when a GPU comes along and asks you, please subtract these gradients from my parameters, then you just then you don't accept new requests until you've subtracted it. So we can do that, and that actually doesn't slow everything down a lot, because the subtraction is a really, really fast operation. So waiting until subtraction ends is really fast. So that actually doesn't slow us down. But there's still a problem, even if our subtractions are atomic. Yes, exactly, Traveler. So we see that here, our training step didn't take into account this new information. So this training step done on the second GPU, it was based on outdated data. So by the time we add new parameters, we already had this update, and this update didn't in any way influence this learning step. This is called the problem of stale gradients. So the gradient is stale because it's like long overdue. And this is a real problem, and this trains worse than... So in our usual training algorithm, we have an assumption that every training step incorporates the information of the previous training step. You've done the training step, you have subtracted the gradients, and you're incorporating that knowledge into the next training step. And here this assumption is broken. And that is a real problem, and that is why they didn't, like, the way that they developed this method is actually an interesting story, because there was a professor who implemented this system with all of the necessary checks and all of the necessary locks. And there was a student who was working on a way to speed this up. And the student basically came to the professor and told him that I came up with a way and it works much faster. I just removed all of the locks and all of the checks. And as it turns out, it is a problem, but it still works. So it does detract from the quality of training somewhat, but over time it still converges. So this method, and they called it HOGWILD for this very reason, that like you just go wild and forego all the necessary checks and balances. This method actually still converges to good results. So you can, empirically, they have shown that this theoretical problem of the theoretical problem of stale gradients isn't crucial empirically. Doesn't ruin your training. It wouldn't, the GPU, no, but see, it wouldn't be computing the same gradient twice because it always does take into account, so GPU always does take into account its previous steps. So GPU 2 always takes into account the previous step of GPU 2. It might have skipped a step of GPU 1 or GPU 3. That might happen. But it does work on a new... So the GPU 2 every time gets a new input, because at the very least, it has its own step incorporated. The problem here is that it might not have all four. It might not, by the time it goes to the next step, it might not have all four incorporated, but it has its own step. So it should never get the same input twice, because at least the GPU2 itself has overwritten the parameters. The GPU isn't updating its own parameters. They are updating the parameters on a central server, but they're doing it with the gradient that this specific GPU computed. And the information from stale gradient, it isn't just discarded. So no information is fully discarded here, because we have a guarantee that every computation is novel. So this step never gets the same parameters as an input. And so we have a guarantee that every computation is novel, and we have a guarantee that every computation is added to the model parameters. So eventually all the stale gradients do get into, so nothing is lost. All the gradients eventually do get into the parameters. But there is just a delay between there is a knowledge delay between the GPUs. So the GPU2 will learn about this update only at this stage, which might be a little later than we would want it to. And this is a problem to some extent, but as they have shown empirically, not to a crucial extent. But starting from the same parameters, multiple GPUs may come up with nearly the same gradient. They're updated several times with a similar gradient. Yeah, in a way, does it simulate a larger learning rate? In a way, yes. So I think the learning rate, you bring up a very good point, that a learning rate here probably has to be adjusted to the number of GPUs. Because if you have a lot of GPUs, then you're right that because of all of this repetition, because of this delay, you are going to have something similar to a larger learning rate. So probably maybe you should lower a learning rate when you're using this setup with a lot of GPU. That's definitely a good point. Thank you. So can we have learning rate as a function of how fast GPU computes a gradient? Maybe. I don't think it should be a function of how fast it computes, because if we speed everything up 10x in this system, then nothing changes actually knowledge-wise, process-wise, and so on. It's not about how fast it is in seconds. It's about how long it is in iterations. So the GPU2 gets its information in 2/3 of an iteration after this information has become available. So here the information becomes available, and in 2/3 of an iteration, it gets the next value. Well, I'm not sure how to do this, Anton. So Anton suggests to somehow actually calculate the difference between what we should have gotten if we didn't have the problem of stale gradients and what we've actually gotten, and to take this difference into account. That sounds really interesting, but to me, it's not obvious. How would you go about this? How would you actually calculate this?